Welcome back, everyone. So today we're going to be talking about the Bernstein-Vazirani algorithm. And the Bernstein-Vazirani algorithm holds a really important place in the history of quantum algorithms because of the fact that it provided the first strong evidence of a query separation between what quantum computers and classical computers can do. Now, let me now share my screen and we can jump into the details of the algorithm and why it's important. So again, the basic high level picture of the question that we wanted to ask is it's one about the relative power of quantum and classical computing. And as you recall before, the fundamental question that we'd like to ask is whether P is equal to, or I guess, BPP, or bounded probability polynomial time algorithms, whether these are equivalent to BQP, which is the quantum analog of it. And this, as yet, is still an unknown question. We don't formally have a proof for it, although we've got a bunch of darn good justifications for it. And the first justification really came about because of this result that I'm going to be showing that shows that if you constrain these classes to end up using oracles, then there actually can be exponential or bigger separations between the two. And so the way we'll end up seeing this is the following. So recall that there were a number of different, a quantum oracle is a way of encoding the input for a particular problem. So an oracle, basically what it does is it holds the input that you stick into the problem. And so there's two different types, and the input, I guess, we can envision being just some function. So, standard function, most of the time, these functions will end up taking the form f maps some bit string to just a Boolean function over here. So a common example of this, would be a function that computes the entries of a string, for example, and outputs the particular bits of that input to the function. But there's many other different types of oracles. And again, we took a look at three different types, actually, of oracles that are commonly used in quantum. The first is a bit oracle. And the way that the bit oracle ended up working was it was OF acting on an input of X and Y. We'll map that to X and Y exclusive or F of X. And then the second major type is a phase oracle. And this phase oracle doesn't need a second register. It will just end up mapping this to, in general, e to the I f of x times omega x. But for most of the cases that we care about, omega will be pi, and this function will just end up becoming -1 to the f of x. Okay, so these are the two classes of oracles. A bit oracle can actually, a single query to a bit oracle can simulate a query to a phase oracle we showed. However, we need a controlled phase oracle to simulate bit oracle. So in general, the bit oracle is more powerful. So if I end up assuming a phase oracle for a particular form, particularly a phase oracle that has a -1 phase, that's usually going to be a weaker assumption than assuming my quantum analog of the classical oracle is a bit oracle. Okay, so now that I've reviewed that, let's go on and take a look at a problem where we can show this separation. And this problem is, as I said before, the Bernstein-Vazirani algorithm. Or the solution to this problem is the Bernstein-Vazirani algorithm. And the idea behind it basically is that what we have is we have some hidden string S. And our goal is to learn S using an oracle that's of a slightly different form than the type that we talked about before. Our oracle function will end up taking any input x over here and map that to x dot s mod 2. So just to give you a particular example, what I mean by that is, let's imagine that I input the bit string x equals 1111, and s was equal to 1011. Then x dot s would be equal to the dot product between these two vectors, which is 1 plus 0 plus 1 plus 1, where I've just taken the product between all of those individual values and take the result mod 2, which is equal to 1. So that is how what this function ends up doing. And so classically, n queries are needed to learn S with probability greater than 1/2. But quantumly, we will require one query to a phase oracle to learn with probability 1. So that's a big difference in terms of the query complexity for it. The query complexity for the classical analog is linear in the size of the input. The quantum query complexity is constant in the size of the input. So this is actually better than an exponential separation. This is a super exponential separation in query complexity. And this is relative to the best classical algorithm that's even randomized at that. So how can we end up seeing it? So first off, let me go through the classical, the details of the classical lower bound. So the classical lower bound works as follows. Imagine that that we have the bit string 0. Well, in order for it to work with probability 0, we really require it to work with probability 0 for all inputs, with probably half for all s, I should say. So then imagine that we, just for simplicity, we take the look at the easiest possible case, which is the case where s equals 0. Now, in this particular case, f of x equals 0 for all x. Why? Because f of x is equal to x dot 0, which is always just going to be equal to 0. Okay, so we have this this particular situation, and so assume that what we end up doing is we end up going through and we end up querying every single possible bit string that we could, or not every bit string. Let's assume that what we do is we go through and we query n minus 1 times. So in that case, we can assume that we use particular sets of values, j0 through jn minus 2 as the inputs to f. So in all of these cases, we're going to find that f of j0 equals f of j n minus 2 equals 0. Like it's going to be 0 for all of them because x dot 0, well, it's always going to be 0. Okay, fantastic. So one of the things that we also get from this is that because of the structure of the algorithm, we have that f of j I XOR j also equals 0 if f of j1 equals f of ji and jj equals 0. Okay, so if we got any two of them and individually they have a dot product with the hidden string of 0, then if we take the exclusive or, because the dot product distributes over a sum, we end up actually finding that that the result is also going to be 0. Why is this important? Well, the reason why this is important is that we can think about the situation that we're doing as a system of equations. So let's just give a particular example. Let's say that what I do is I have J1 or J0 equals 1, 0, 0. J2 equals 1, 0, 1. And J3, let's pick it to be 1, 1, 1. Okay. Now, what I can do is I can say, okay, well, all of these things are going to be, this is a system of equations. In the system of equations, we can write as 1.s0 plus 0.s1 plus 0.s2 equals 0, mod 2. And, 1.s0 plus 0.s1 plus 1.s2 equals 0. And so we can write this system of equations using, standard in a standard like row echelon form for this as 1, 0, 0, 1, 0, 1, 1, 1, 1, 0, 0, 0. And now, because of the fact that we can add different equations and the sum of it for the modular arithmetic for this problem that we're interested in, because the sum doesn't end up changing the solution, that corresponds to us being allowed to add any two of these vectors together, and it won't change the structure of the system of equations. So we can go through and, for example, add row 1 to columns 2 and rows 2 and rows 3. This will end up giving us 1, 0, 0, because we haven't done anything to the first row. Now this will give us 0, 0, 1, 0. And then this will give us 0, 1, 1 over here. So now if we continue the row reduction, this will end up then giving us 1, 0, 0, 0, 1, 0, 0, 0, 1, just by adding together different combinations of these rows. I'm sure you've done this a bunch of times, so I won't bore you with the details. So this is the matrix that we end up getting in the end. This matrix then implies that S1 equals 0, S2 equals 0, and S3 equals 0 is the unique solution to it. But let's imagine that we didn't have enough rows and columns to be able to specify it. If we didn't have enough rows and columns, then what we would have is, say we didn't have this result down here. We would have these two results only. And from this, we don't have enough information in order to be able to determine the middle bit. The middle bit over here could be either 0 or 1. So this system of equations, if we're missing one row, actually any deterministic, any randomized algorithm that we would do in order to try to guess this value of the missing element will succeed with probability 1/2, okay, which is against the assumptions of the theorem or that we require, because we require that it has probability greater than 1/2. Okay, and in general, the exact same procedure ends up holding if we have not two equations, but we have n-1 equations and n unknowns. The best case scenario that we're going to have is that, there's going to be one variable out of that isn't specified by this, by the row reduction process. And that means we're forced to guess, which will imply, just like we had down here, that the success probability is 1/2 for everything. Ergo, the best that we can do is n queries with probability, if we demand probability greater than 1/2. And in particular, you can see that n queries is sufficient because once we have n distinct numbers, then we can carry out the full row reduction and end up solving the system of equations because we've got n unknowns and n equations. And since the sum of the two solutions, and even in this discrete case, is also a solution, we can apply the Gaussian elimination algorithm to solve for the solution. Okay, so this shows that we can't possibly do better than n queries if we want to have success probability greater than 1/2. So quantumly, how does this end up working? So quantumly, the way I'm going to show that we can have an algorithm that will require one query. Also, you can see in terms of query complexity, that's optimal too. Why is that? Well, okay, the only way that you could do better than one query is if you use 0 queries. And then there's no information about the function that's coming into your problem at all. So this algorithm not only requires one query, but it's also optimal. Now, the way the algorithm ends up working is real similar. And I'm going to assume specifically that we have a phase oracle here. And the way the phase oracle is going to work is that we will take -1 to the x multiplied by x for any input. Okay, and this is the OF that does this. So the quantum algorithm drawn as a quantum circuit works like this. We begin by setting all the bits to 0. We then apply a Hadamard transform to each of the individual bits. We then feed in the result into our oracle function. We then Hadamard transform. I know, right? It's so predictable. We always begin these algorithms by applying a Hadamard transform. But there's good reason for it, because we need to, again, break up our problem into a superposition of different paths and use interference between those paths to compute the result. But in any case, this is the entirety of the algorithm. Now, the question is, oh, it's just -1 to the x. It's -1 to the f of x. What's the intuition behind this? Well, one of the big intuitions behind this ends up coming from the structure of the Hadamard transform. Recall that the Hadamard transform satisfies HZH equals x. So if HZH is equal to x, what we can see is that this over here is like a phase flip. It's 1, 0, -1. So we can think about this as kind of a phase oracle. And specifically, the phase oracles of the form f x goes to -1 to the x. So in this case, f of x is just equal to x. So we can see that the Hadamard transform can transform this particular phase oracle, i.e. the Pauli Z game, into a X game, into a bit flip. And that's what we're using in order to be able to identify the hidden string that's going into our oracle, where in this case, this is -1 to the s dot x. Okay, so in order to understand how this works, there's a property that I think I talked about last time, but let's go over it again, that we're going to use. The property is that the Hadamard transform, tensored n, acting on some unknown state x, is equal to the sum over j, 1 over root 2 to the n, -1 to the x dot j, j. Okay, now how can we end up seeing this? Well, it's actually not so bad. The way that we can end up seeing this is that we have Hadamard tensor n acting on some bit string. Let's imagine a bit string is of the form x0, x1, going all the way down to xn -1. Okay, well, this is going to map us to 1 over root 2 to the n. 0 plus -1 to the x0, 1, tensored with 0 plus -1 to the x1, acting on 1 over here, and going all the way down to 0 plus -1 to the xn minus 1, acting on 1. Okay, so now we can consider grouping all of these tensor products together. Using the distributive property of tensor products, we end up seeing that if our bit string is of the form, if for every 1 that we end up getting in our bit string, we'll get a corresponding value of -1 to the x0 coming in from one of these guys, which is always associated with a value that's 1 in this case. So in general, basically for every position, there's a 1 in the binary representation of a number that comes out of this product over here, we're going to get a factor of -1. So in general, actually, this whole expression that we end up getting means that for every j that we end up getting, the coefficient is going to be -1 to the x0 times j0 plus x1 times j1, going down to xn minus 1, jn minus 1, all times j. And that is the exact same pattern that we see here. So in general, Hadamard tensor n acting on x ends up giving us this quantum state. Let me just copy this for a moment, and then we can go on to the next slide. All right, so here we go. This is the fun expression that we have. But there's something really kind of cool about this that we'll see in a second. This identity is actually going to allow us to see how we can immediately determine the oracle. And the hint about why this is true is let's just look at what OF does. It acts on X and maps this to -1 to the X dot S, X, which is the exact same structure that we see here. And so if we plug this in to our quantum circuit, which again ended up looking like following, what we get is the very first stage is we have 0, tensor n, maps to 1/√2 to the n, sum over j, j. Now we can see this because the input is 0 over here, and this corresponds to x equals 0. And so just substituting that value in this expression gives us this. Alternatively, you can see how the distributive property ends up going. It's clearly just a uniform combination of everything in this case. So anyways, we have 0 tensor n maps to this guy over here under Hadamard tensor n. Now, what does OF map this to? Well, OF is just going to put a -1 to the x dot s in there, or j in this particular case. Okay, so we can see actually just from pattern matching between these two that this is actually equal to Hadamard tensor n acting on a bit string containing s. Therefore, if we apply Hadamard tensor n acting on this particular state, we end up getting Hadamard tensor n acting on Hadamard tensor n s. These two cancel, and the state that we get is the binary string s, where, just to be clear, this is the bit string s0, s1, going all the way down to sn minus 1. So at the end of this algorithm is 100% deterministic. The hidden string that we wanted to learn is just sitting there for the taking immediately after you measure each of these bits over here. Okay, so in a single query, we've achieved what provably requires, at least with probability greater than a half, n queries on a classical computer using the optimal possible algorithm. And this shows that quantum is actually capable of doing something that is vastly more powerful than what classical can do. However, it's not terribly useful, everything considered. Very few examples of problems that can be mapped down to this problem of identifying a hidden string. And so in the next couple of lectures, we're going to begin by building a richer set of algorithmic tools that aren't designed just to show an advantage, like this case is over here, but to actually help us practically solve hard problems. So thank you very much. I'll see you all next time.